session especially is in alignment with the key topic of this year's Capella Days, which is industrial experience. And from Rivada Space Networks, I wanted to share as to how did we tailor MBSE and Arcadia for a complex groundbreaking space program. The agenda follows 4 parts. First, I'll take some time to introduce exactly who we are and what we are trying to build, which is called the OuterNET. Minded, I'll keep saying RSN, but that's the abbreviation for Rivada Space Networks. The second part is for MBSE implementation, the strategy. Here I'll talk about what drove the need for it and the scoping activities we did. The third part is on the actual implementation of MBSE within the engineering workflow. I'll walk you through the model initialization step we did, all the way with some use case examples. And lastly, I'll share some lessons that we have learned so far from our experiences. Who we are? Well, Laurent already introduced us, but I'll do it again. Firstly, I'd like to mention Vincenzo. He has since parted ways with the company, but Vincenzo was the systems engineering manager who was responsible for deploying MBSE and building the team around it. And I'm Sahil, Metta, the model-based systems engineer over here. We are headquartered in 2 locations, Munich and Berlin, and we have about 150 employees across 31 nationalities. In my opinion, this is quite great because we are quite a diverse group. And most of our employees are situated all over the world. We have over 300 years of collective experiences within the satellite and wireless industries. This is thanks to most of our experts are coming from the leading companies in these industries. Now, when talking about a new product or a service, personally, I would like to talk about the challenges it's trying to solve. And this is pertaining to the global telecommunications in our case. This list is in no priority order, starting off with cybersecurity threats. Well, in my opinion, not only a complex system, but even a simple system that is being developed nowadays has to go through the lens of cybersecurity. Lack of coverage. I'm sure most of you have experienced a no signal notification at some point in your life. This is also true for enterprises and businesses when they are moving to new locations where there is a problem of lack of coverage. Network fragmentation, data sovereignty, especially in this geopolitical world, this has become an increasingly important factor where some nations are also seeing it as a national asset. High latency. I'm sure no one wants the YouTube videos to keep buffering, and for that you would prefer low latency. No end-to-end quality of service assurance and lack of scalability are some other challenges that global telecommunications is facing. To solve these problems is what RSN is building and what we call the OuterNET. It's truly a private network in space. RSN is revolutionizing the global connectivity by making this very unique gateway-less satellite constellation in the low Earth orbit. The orbital network itself is what we are calling the OuterNET, is first of its kind. It's purpose-built to transport all the customer's data end-to-end, meaning if a terminal in Melbourne wants to connect to a terminal in UK, the terminal in Melbourne would send that data to a constellation of satellites, and that data will traverse in space all the way to a satellite that's servicing UK at that time, and it will go down. Now, to enable this kind of services, you need a quite big infrastructure. And for this, we'll be having 600 satellites in the low Earth orbit. Now, these will be launched in 2 generations, Gen 1 and Gen 2. We'll be operating in 24 polar orbital planes with 24 satellites in each, and at an altitude of 1,050 kilometers. For me, the best way to imagine the whole system working together is to look at the animation at the back. You see there's a fishnet type mesh over the globe. Now that is how you can imagine our system will work, where the nodes, the blue dots, are representing the satellites. And the blue threads that are joining all these nodes are what we call the intersatellite links. And we will have about 2,000 of them. So by design itself, we are achieving highest security possible because once the data enters our network in space, it stays in space from origin to destination. We are even providing global connectivity. Now this is thanks to the fact that we are having polar orbital planes where we can even service poles and sea. Data sovereignty, as there's no connection between any third party during the transport of the data. Ultra low latency and high throughput, we can achieve these things. As you can see, we are 10 gigs per satellite throughput, and we are using the K band, utilizing 4 gigahertz in this spectrum, which is very important for high throughput. And of course, plug and play is a very important factor, especially in respect to how the customers get onboarded with the network. And this is a very key factor when we are developing the system. Hopefully, I did a good job explaining what we are trying to build. Now, coming on to the MBSE implementation strategy at RSN. The first step is the need. What was the need for deploying MBSE? Well, there were three main factors that we looked at. First factor was that this was a groundbreaking space project, meaning we don't have any references or prior programs to look at for this. And in a context, we had to develop it at a much faster development pace compared to any traditional space program. And this is heavily time constrained. From the system engineering point of view, who needs to take care and mitigate risk as much as possible, we need to be as effective as possible. And for this, one of the main steps to do is to go digital. The second factor is that there's a wide range of subsystems that will be involved, and they're geographically distributed all over the world. This is adding the complicated part. What we need is a single source of truth for many reasons, for proper coordination, to have effective dependency establishments, and many more. The third factor is that it's a truly unique system architecture in my point of view, because there are n number of new technologies that are still undergoing development, and they need to be deployed within the system for the system to work. So from the system point of view, we need to have the system control for managing the emergent behavior, which is the kind of uncertainties that are induced due to factors like technological advancement. What we really care is the famous three C's: consistency, correctness, and completeness. And in a context of building a complex system, where there are multiple teams involved across multiple disciplines, and this all needs to be done in a less time because time constraints, RSN needed to go the model-based engineering way. Now, using this V model, which is superimposed with the various model-based branches, you see that MBSE is coming on the left-hand side of the V on the early stages of requirements and architectural definitions. And as you go towards the right, you reach the model-based verification and validation. For us, when selecting the method and tool, we also looked at the three key pillars. The method, which in principle is giving a guiding principle as to how to architect the system. And for us, the main feature over here that we are looking for was the customizability we can do for our project needs. On the tool pillar, a tool is basically what a system modeler would use to make these coherent set of system models. And for us, a very important point was minimized upfront investment in terms of both time and resources. And on the language side, of course, being a subset of SysML, we assumed that the learning curve would be much relative faster. And especially by attending this session, I'm sure most of you can guess which tool and method we went for. It was Arcadia, the methodology and the modeling language, and Capella, the tool. Now, talking about the MBSE deployment strategy within the organization, the peculiarity of our organization was, from the organizational point of view, it was already clear that MBSE is required. So we could more focus on the implementation first approach and derive some key strategies. The first strategy centered around defining and communicating a clear scope tailored to the organizational structure. What I mean by this is we needed to have an organizational view, which is imperative to assess what processes are already in place and where the value needs to be added. And also we had to align MBSE to the RSN's global philosophy, which is it is heavily reliant on procurement oriented, and co-engineering with partners is of heavy focus. The next strategy was retrofitting documents to reflect prior design decisions. Yes, in our organization, MBSE was implemented a bit midway of phase A0 like status of a space program. So it required a strategy of its own to transition those design decisions into the modeling language. Harmonizing engineering workflows, well, the key word that comes here, which is always tough to pronounce in my opinion, is interoperability. Basically, which means is how seamlessly we can integrate two tools and have data exchanges between them. For us, in specific, among all the organization tools, it was important to have this chain developed with the requirements management tool that was already in place, which is Valley Space. Now, also establishing system functional design via use cases was a completely MBSE-driven approach, which was thoroughly defined by us and adopted by multidisciplinary teams. Now, as you can see, to address the specificity of our project needs, we had to scope MBSE in a correct manner. And to show how we scoped it, I've used the synoptic view of Arcadia. I'm sure most of you are well versed with this kind of view. But for those who are not, row-wise, you are basically seeing the different architecting layers that are defined in Arcadia. On the operational analysis layer, you have where you're understanding your stakeholder needs and you're aligning your business plan. And as you go down these rows, you're basically refining your architecture. And column-wise, you're seeing the different artifacts that are used in different system engineering phases within Capella. The requirement side is where we understood would be handled by Wally Space. What was essential for us was that we had to develop an interoperable chain between Wally Space and Capella. And for the interfaces side, we understood that it was easier and best decision to be that the detailed design of the interfaces follow the traditional ICD processes, but Capella started facilitating the interface identification activity and populating them. But this is how, for us, each layer actually meant. And as you see, purposely Capella was kept out of scope of operational analysis layer because here is where you're understanding the business and the mission analysis phase. But for us, in the prior work that was already done, this was well documented. And for time priority basis, we had to go to the solution domain as soon as possible. Hence, the system analysis layer was the perfect place where we merged these documentation and then we went down the solution domain. Talking about the RSN's ecosystem from the MBSE's point of view, for us, the solution domain, OuterNET, was a system of systems. The goal for us was simple: design an architecture of the system that is defining the functions and interfaces for each element. Well, it's simple but very complex to do, I must agree. To address you how the abstract view of our whole RSN ecosystem, the first layer in the horizontal side was a system layer, which is taking care of the functional architecture at a high level, including the breakdown and the product tree, the requirements, and especially the traceability back to the services in the need domain, and the system interfaces. There are three other horizontals, which I'm sure the space colleagues in the audience can recognize. The GS standing for ground segment, S2 standing for space segment, and US standing for user segment. Each of these segments are responsible for their own functional architecture, requirements, interfaces. But the way the whole system is getting orchestrated, that's the system layer's responsibility. The system layer is taking care of the integration, consistency, and so on. But the way they interact with all the segments, here is where I use the system engineering disciplines, where MBSE, requirements management, interface management comes into place. But the truly unique part of the OuterNET are the technologies that we are employing. These technologies, as you see, are purposely in a vertical direction. They're transversal to all the horizontals. The technologies being network engineering, security, RF communication engineering, software. They have to be custom built for our system to work. The question is, how do we capture that these technologies are properly captured around the segments? You have the design concept, for example, for the network. You have the network design concept. You need to translate that into a set of functional needs from which you're deriving the functional requirements allocated to functions, which is allocated to logical components that are spread across these segments. Also, operations was a key layer. Rivada would be a future operator of the system ourselves, so it was important to have the operations point of view while developing the system. But for time priority basis, this was kept out of MBSE scope, but taken care of other system engineering processes. The whole ecosystem needs to work in a well-oiled machine manner so that we can make a very informed procurement make or buy decision. And as you can imagine, there's a lot of cross-functional activity that needs to take place. And for addressing this, MBSE proposed the use case-driven approach. We also developed the interoperable chain between Capella and Wally Space to facilitate this complex system activity. The MBSE model in Capella, which is taking ownership of functions, system components, and interfaces, whereas the requirements are managed in Wally Space. When we have this whole ecosystem working very well, you have the benefit in scenarios where when a vendor is coming back with a non-compliance on certain functional requirements, within RSN, you need very strong processes that are relating to impact analysis in place so that we can assess exactly what kind of system capabilities, services, functions, interfaces, and so on are affected. Now, this is only achievable once we have this whole ecosystem working in a very rigid manner. That was how we implemented and the strategies around MBSE, but actually how did we start introducing MBSE into the workflow? The first step was the system model initialization. At T0, the initializing activity required the retrofitting of technical documents, mainly the system design definition document, which was baselined in the system baseline review, into a modeling language. Side by side, alongside this activity, also how to tailor Arcadia and Capella was a key strategy to be made. The very first diagram that you go for in this scenario is, in the system analysis layer, we went for the MCB diagram, going for the mission capability diagram. Here you see the key capability, which is provide connectivity services. Now this is the main system of interest purpose, the system of interest being the OuterNET. On the left-hand side, you see the external actors, and you want to understand how they're interacting with our system of interest. These actors are not only your customers, but also regulatory bodies, law enforcement agencies, and so on. On the right, you have the various type of services that we wanted to provide to our services, to our customers. Now, what we did was, you want to translate these into system missions, and these system missions in SL layer are identified as system capabilities that are needed to deliver these services that we have. And when transitioning them into the LA layer, we convert them into capability packages. And these capability packages are consisting of capability realizations. Now, this is also coming as an output of the retrofitting activity. Each capability realization is further broken down as logical functions at the LA layer. And in the LA layer, the logical components are kept at the segment level. And when we are doing the segment to element level detailed design, this is happening in the PA level. The whole idea of the whole workflow are two. The first, that the OuterNET should be pictured by a certain number of system capabilities that we can control. And each capability should be defined or described by a set of identified use cases, which will be illustrated in terms of functional chains or sequence diagrams within Capella. Now for this, there were two main concurrent technical activities MBSE team had to propose to perform the system functional design. The first one was the use cases and use case scenarios, and alongside that, the functional analysis on the requirements documentation. The use case activity is helping us understand how the OuterNET is going to work. And at the same time, the functional analysis is going to make sure that the design that we are understanding is translated into a set of requirements which are complete, correct, and consistent. Now, this is very important because, as I said, we are heavily procurement oriented, and the requirements are the interface for that. And that is why it should be a concurrent activity. Now, from a use case, you understand which functions are to be performed by which element of the system. And at the same time, you're going to see that all the needed functions that are identified are specified in a set of dedicated requirements, and vice versa. A use case is not only telling about what functions are there, but it's also saying how they're interacting to deliver a certain kind of system capability. Now, this is giving rise to identifying the interfaces. And this is also what you need to translate into a set of technical specifications that are representative of the design entirely. Now, to go a bit more detail in this workflow, and especially tell you how the MBSE and MBRE model-based requirement engineering world coexist in RSN. The first step is the programmatic work. Now, over here, the output that we are expecting is that we get a complete list of use cases which are very much aligned with the programmatic schedule as well. This gives very important details as to even the priorities for the use cases. Now, from the use case list, each use case has a use case owner. The use case owner works with the MBSE team and also facilitates the technical discussion with the system architects. Now, these technical discussions need to be translated into two worlds. On the modeling world in MBSE, these technical discussions are translated by baselining the architectural designs via use cases. And in the requirements world, they need to be translated into a set of requirements. So coming to the use case world, the kingpin artifact that we have is the use case, which is described by functional change or exchange scenarios. Both are involving a similar functional design block, which in essence is containing a list of functions, a list of functional exchanges. Function is assigned to a functional component, whereas a component exchange is assigned to functional exchange is assigned to a component exchange, which in respect are the identified interfaces. On the requirement side, there are two branches that are of interest. First, when we look at the type of the requirement, we see globally the functional and the non-functional. And you see the product tree allocation, where you get the applicable component specified. The interoperability chain that we created is logically the green lines that we have here created. And this is thanks to PVMT and Python for Capella. So on the MBSE side, the functional components are referencing to the product tree and making sure we are referencing to the correct component. And from the requirements point of view, you can see the type functional requirements are directly having an association with the function. So talking more about this green lines and how we build them. Well, yeah, we also had a situation where actually our requirements engineering tool, Wally Space, was actually non-compliant to OSLC. But still using these add-ons, we were able to create an interoperability tool chain. And how did you do that? Is that we have the model from which you can export different kind of data set. Here, for example, let's take functions and functional attributes. This is sent to a database. Now in this database, you get the new data set, and you also have data set coming from Wally Space, which is giving you the existing functions that are there. And with Python for Capella, we can make some basic operations of checking the added functions, the deleted, the renamed functions. You get the most updated set of requirements sent to Wally Space. And in the requirements tab, you see that we have a custom attribute for function requirement created that is function. Now this is one directional, but what is very significant for us is to have the bidirectional capability, where we even make an assessment of if a requirement is having a function or not. If it's not, it makes a technical decision as to if the requirement is obsolete or the functional model needs updation. The allocation activity is to be performed by a subject matter expert in Wally Space for each requirement. And the bidirectional link is highlighting the justification for a function or a requirement. I'll go a bit fast now because we have only 5 minutes left. But to give a practical example on the use cases, we see it in two levels, the high level view and then the low level. MBSE activities are at system level, which is very important and scoped in our strategy. A use case at system level for us is incorporating several technologies that are interfacing between various segments to come together to realize a very specific objective set for a particular use case. Now, for example, you have two technologies that need to be employed in a certain way so that the user terminal on ground can connect to a satellite. Technology A being developed by team A and technology B developed by team B. They have their own set of documentation. To merge them, we facilitated this with an exchange scenario diagram when the temporal factor is very important. Now, this kind of activity helps facilitating a clear visual representation of the merged concepts. It enriches the cross-engineering discussion and then eventually acts as the single source of truth. And by this high-level activity, we are able to identify the components that involve major functions and major functional exchanges. Once reviewed and agreed at a high level, we then go on to do the low-level approach. Well, exactly how we define the low-level design is not the objective of today's presentation. But what is the key goal you're coming out of this is you have the P.o.V diagrams, which is not only having many exchanges, but is also having much more details in terms of the artifacts that are used, component exchanges, exchange items. We need to make sure that all this design is translated into a set of requirements. And this is thanks to the interoperable chain we have built. The key goal from this activity is we are able to identify the exchanges, interface flows, exchange items. And this, in long run, is facilitating the automatic validation of the completeness of a functional design, the use cases with requirements. Coming to the lessons learned, I would talk about the domino effect. The domino effect as a system is where any system where you put an impact and you can kind of gauge the propagation of the impact. Now, for us, this happens quite frequently. For example, when there's an impact due to a technological redesign, this could happen due to many reasons. One of the reasons is a major engineering trade-off leads to an alternative design concept. Now, how do we take care of this? What are the actions to take care? We can use the customized traceability, which is giving a clear system-wide view, and this helps team assess the technological impacts on each subsystem, and this then affects how they give response to these changes. So in terms of Capella, you will see this redesign, the technological redesign impacting in terms of functions, interfaces, use cases, which is then translated in a report, which gives key information as to which functions exactly are affected and at system level, exactly what use cases are being affected. Coming to the almost last ending of my presentation, some challenges and solutions that we saw. Well, climbing a hill is exactly how I felt when I'm talking about challenges. Some of the challenges were, as we are adopting a new way of design process over here for many of the engineers that were here, a lot more systems thinking is required. The scope of MBSE itself is very large, and it is very critical that we find the relative value to the project scope that we have. In our case, also integrating legacy products into the model was a challenge because we were a midway implementation. And then the quantity of data to be handled in model. This is directly proportional to the granularity that we are specifying in the scope of MBSE. The upfront investment in both in terms of time and resources is to be taken care of. I'll skip the next two challenges, but coming on the solution side, the practices that we really felt worked for us was to educate and train an initial cadre of modelers from different multidisciplinary teams. This starts helping to talk the same language. Well, also scoping your MBSE activities clearly in a set of documents or presentations organization-wide is very key to have. Well, MBSE itself, the main objective is communication. That's the key. And for us, to develop system models that have immediate benefits to the project needs is important. And this also leads to model only what you need at a given time. Then, I'll go to this point. Partnering modelers with system architects early on was a very big benefit. And the way our mindset was to see MBSE implementation as an evolution and not as a revolution. Before ending, I will even share some system-wide KPIs that we tracked. On the functional analysis in terms of matrices, this type of matrix was a direct output coming from model, where you have attributes such as functions, requirements, use cases, and some more. This helps us directly highlight the gaps that are there, and you can tie these gaps in action items to future milestones. This is a completely incorporated process within RSN, and it's a bit system-wide KPI. An internal KPI to MBSE is to maintain the model quality and validation rules. To perform these automated checks, of course, because we have customized Arcadia quite a lot for our project needs, we had to write our own validation rules, and that was effectively done via scripts, which helped us highlight discrepancies like duplication, missing traceability, and more. And this is something we do periodically within the MBSE team. With this, I come to the end of my presentation. Thank you for your attendance, and I see if you have any questions, I will take and try to answer them.
Thank you very much, Sahil, for this very well-built presentation. Very interesting presentation. I have a question on the methodology approach that can be used to develop a space system. For example, let's say some countries trying to use nuclear weapons in space are a threat to other countries. The UN treaty needs to verify it, so a system engineer project arises to develop a verification system for this. Which starting approach would you suggest when developing a space system like this? It looks like a consulting question.
Yeah, quite a specific question, I must say. Very interesting. Well, I don't know if you're going to, well, if I read the question again, I don't know if the question is actually we need to develop a space system for this, or it's coming more at the regulatory. Interesting. Well, I see the main, I'm not no consultant, but what I'm seeing is the first step to see is you need to refer to the existing UN treaty and all the regulatory needs. And from then, that would be the primary input, and then you start building your system from there. Well, I'm not very sure about exactly what kind of regulatory needs would follow this kind of scenario, so I cannot give you much guidance over here.
Let's move to the next question then. Thank you for a very well-structured presentation. I agree. What are the main challenges you currently encounter when moving from system design level to domain-specific implementation handoff? And have you encountered any major benefits, or the contrary, when using MBSE with Capella?
Yeah. Well, if you remember in my presentation, one thing is very clear, is that we are very much procurement-oriented. So many times, we are making sure that at system level, we are understanding what our system is doing. So this leads to that we don't jump to our implementation phase right on every subsystem. We are still trying to understand the whole system level approach. And then, if needed, and some of the subsystems when built within RSN, then we'll go to the implementation handoff strategy. And on this point, major trade-off. Yeah, I feel the benefit of doing the way we have done is that at least at a system level, it's quite clear. And having Capella and using the subsystem to system transition, we can, and in the subsystem level, that's where we would say that that's where the implementation type of designing would go forward. So this kind of approach using Capella and MBSE really helps over there, where you can track directly the implementation level design to the system-wide level effect it will have.
Okay, thank you very much. Let's move to the next question then. How do you build, if you do you build cybersecurity and continuous threat risk analysis into your MBSE approach?
This is a very good question. This is a question we really look forward to and we are trying to implement within our company right now. Well, of course, we know there are a few very important add-ons regarding this cybersecurity for Capella in specific. But currently, our security team is is working with another, let's say, add-on. So we have had exchanges with them, and we see there's a lot many, let's say, bridges that we can actually directly implement it in MBSE itself. But this is right now happening outside MBSE, so I don't know if I can answer the continuous threat analysis part, but this is something we can and we will do later on.
Thank you very much. And then this question, what percent of RSN is versed in MBSE? Could you comment on having an organizational-wide understanding of the MBSE technology, methodology, I mean?
Yes, but good question. Well, this was one of the main challenges which I didn't really mention is we have a lot of experienced people from the space industry, wireless industry, who are not maybe very much aware of MBSE, it being something that's implemented in the last 20 years. But there's an openness of learning. So there wasn't a lot of people who knew MBSE right from the beginning, but there was an openness to learn MBSE. And at least from the organizational point of view, we had the mandate that certain instances within the project needs to happen with the MBSE process in place. So this helped enforcing MBSE system-wide. So you need that organizational mandate with you. And slowly, in my opinion, actually MBSE has great value. And when engineers are actually working with MBSE, they truly start seeing the value it's bringing to their own work. So in that sense, the percentage was quite low. It has gone to about, let's say, 60%, about 70 it's reaching. But from there to go up to 100% is much slower than going from 30 to 60, I would say.
Okay, then a last question. I think we have time for one last question. So do you consider that implementing MBSE at early stages in space systems reduces the amount of FTE needed for phase A?
I would say instantly yes, because of the bias of having MBSE. Well, MBSE helps you mitigate risks later on in the project. So automatically you would imagine you could have a reduction of FTEs, but not in phase A, I would say, but at a later phase. But for sure, having MBSE implemented early on in space systems, or to be fair, in any complex systems, is quite beneficial. It's tough. Well, I would say it's always tough to gauge the return on investment on system engineering or MBSE per se, because you cannot track something when it's not there and something when it's there, because MBSE is continuously highlighting these gaps. And this in relation is helping you avoid these errors later on.
Okay, thank you very much, Sahil. Maybe one last question from my side. What do you think in what you presented is really specific to the space domain and what could be reused in other contexts than space-specific domains?
Well, to be fair, when me and Vincenzo created this presentation, it wasn't actually very... we kept in mind that we didn't go, as you see, much detail into what we modeled. What was more in focus was the processes. Well, from the way of concentrating on how to scope MBSE, because as I said, MBSE itself is quite big. And in many projects such as this as well, you have engineers who are not that aware of MBSE. So enforcing MBSE at every stage doesn't really work. So you need to focus on gradual infusion of MBSE and And that was kind of the message we wanted to put forward, that focus on the scoping, then focus on the real benefits that you can bring on at the correct time in the project, not at some other later time where no one is looking at your MBSE model anymore, which is quite a pitfall many times I think people feel. So to avoid these things, we focus more on being very pragmatic, as pragmatic as we can, and also see early on the later stages where we can actually have strategies in place. So, for example, someone raised the cybersecurity question. Well, that was in fact one of the key strategies we already have in place. As to later on, if we want to include it into MBSE approach, we have a strategy that can be done. So this would be my answer, and that was the reason behind our presentation today.
Okay. Thank you, Sahil. See you later.
Thank you. Bye-bye.
Bye.